Good morning, everybody in the lecture hall. Good morning, everybody on Zoom. Good morning, everybody watching us from the future. Today we are in the middle of the semester and the data is flowing like crazy on the cluster of machines, petabytes of data in the network cables with MapReduce. And we've seen that because of so much data flowing in the network cables and so much data read from this, we need to have optimizations known generally in big data as push-down optimizations. It's everything that can reduce the traffic jams on the network cables or reduce what we store on disk either as input or intermediates. So my question to you is, among these 5 possibilities, which ones of them are push-down optimizations in the sense that they reduce the traffic jam on the network cables and on disk? So we have 5 possibilities. The first one is projecting away unused columns, fields. The second one is materializing a logical structure on disk explicitly and physically. The third possibility is pre-aggregating values, for example, combined functions. The fourth possibility is batch processing, flushing and speeding or compacting and merging. Does that reduce the data on the network? And the fifth possibility is filtering unused records, for example, that you know will not be needed later. So which ones of these are? Oh, I said not push that. I realized I inverted the answers in there. So which ones are not push-down optimizations? Maybe I still have a chance to change what is correct and not correct. Exactly, I've done that. And now I can show the responses live. Exactly. So I'm asking for the ones that are not push-down optimization. So we have majorities, it seems. All right. And these two were the correct answers. So the majority wins. Indeed, it's all about thinking what reduces the amount of data, right? So if you project away unused columns, that reduces the amount of data, right? You have 10 columns, but you only use 2 later on in the cluster, then you can just project them away. It means that you project to the complement, projecting away. So that is a push-down optimization. Pre-aggregating values is a push-down optimizations. You basically squeeze several key values into a single key value where you pre-aggregate the value, like Pokemon 1, Pokemon 1, Pokemon 1, Pokemon 1, you replace with Pokemon 4. So that also reduces the bytes that go on the network cables. Filtering unused records, that also reduces, although we didn't see it specifically in MapReduce, right? But imagine that you have a huge table with billions of records, and you know in your query that somehow you have a filtering somewhere. That means that you're only considering, for example, it's the entire population in Switzerland, but you only want the people in a certain village. Well, then you can already filter it very early when you read from disk. Already at that moment, you can just throw away everything that you don't need. So you can push down a projection or push down a selection or push down a pre-aggregation. That's basically 3 of the possibilities. Who agrees that this reduces the bytes on the network cables when we do that? Right? Because we get rid of data, right? The other 2 do not change anything. Materializing a logical structure on disk, on the contrary, that's very heavy on resources, right? It's called the materialization. We'll see in the lecture what that does and the consequences of this. But materializing a logical structure doesn't remove any data, right? It only will even need more disk space or more memory to be able to do that. Batch processing, we do it, of course. That's how HBase and MapReduce are implemented. But that doesn't that doesn't bring down the quantity of data sent over the network cables, right? The flushing and speeding and compacting and merging, that's only in order to persist data that doesn't fit in memory anymore, right? So that doesn't have any impact on the data sent over the network cables, right? So this is why answer 2 and 4 are not push-down optimizations. Okay, who is with me? Feel comfortable with that? All right. So remember this push down optimization, it is extremely important. And in your future employer, you will be heroes. These are some of the most straightforward optimizations to do. Super slow system, you arrive as the hero pushing down the optimization and suddenly everything is much faster. This is really a very powerful way to optimize a big data system. So now let's continue a little bit on letting data flow in the cluster to evaluate queries. We've seen MapReduce. We saw that it looks like this. We map in parallel, then we shuffle the data around, the intermediate collections of key value pairs, and then we reduce and we have an output collection of key value pairs, right? If I abstract that a little bit away and zoom a little bit out, this is basically what we do. We have a collection of key values. We map them to an intermediate collection of key values, and then we reduce them to an output collection of key values, right? That is the logical view on that. Well, now I'm going to press the button and show you, in contrast to this, what Spark does. And I would like you to tell me 3 differences. Careful, this is what Spark does. So spot the differences, 3 differences between this and this that Spark improves over MapReduce. Do you see them? 3 differences. It's not like the game of the 7 differences in the newspapers where it's very hard to spot, right? There is one difference that already jumps to the eyes here, right? So let me tell you, let me start with one. Here it's just 3 collections of key values. It's just a line, right? Here we have, what is this structure called in terms of graph? This is a DAG, yes, that's a distributed. I'm so used to MapReduce. This is a direct acyclic graph. I never remember what the abbreviation stands for. Directed acyclic graph, yes. So this is a DAG. This is a DAG, and this is not a DAG. So, well, it is also a DAG, but this is more generic than this very specific structure. So that's a DAG. That's the first difference. So Spark turns the whole thing into any DAG, any directed acyclic graph. 2 other differences. Do you see them? Yes? Exactly. We had in MapReduce key values. We needed to hit everything with a hammer to turn it into key values. And now we don't need to do that anymore because we can have collections of whatever. This whatever could still be key values, right? A key value can still be considered a value, right? But it can be anything. So you could have collections of integers, collections of strings, collections of JSON objects, collections of key values. So this is more generic also, right? Because we just have collections of whatever. And the third difference? Yes? Exactly, many more operations. So here it's just map and reduce, exactly in that order. But here you have filter, flat map, distinct, sample, join, reduce by key, map, union. So the menu is much more diverse than in MapReduce, right? They are called transformations, all these things, but I'll drive you through it, okay? So 3 differences from here to here. First, it's not just a 2-phase mechanism. It's a generic DAG, directed acyclic graph, the one I never remember. Second difference, it doesn't have to be key value pairs everywhere. Now we just have anything, even if it's not a key value, that's fine, just a collection of any values. And third difference, instead of just map and reduce, we have a whole menu of something like 30 different transformations that you can put in there. Well, this is basically Spark. This is how it works on the logical level. Now, when I write any values in there, we have a name for them. We call them RDDs. And RDDs means resilient distributed. So this is where the D stands for distributed, resilient distributed data set. But we just say RDD because if we keep saying resilient distributing data sets, that takes time to say, right? So everybody says RDD. right? So these, any values here, we just say that's an RDD, that's an RDD, that's an RDD, that's an RDD, 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 right? Now, why do we say resilient distributed data set? Well, an RDD is in fact a big collection of values, these any values, right? A big collection of values, and it is partitions. It means that these huge collections of maybe billions or trillions of values, in fact, physically, they are spread across machines. Right. That shouldn't be new to you because that was the same in MapReduce, right? These collections of key value pairs, input, intermediate, and output, they were also spread over the machines, right? So that was also partitions. In MapReduce, do you remember the name of the partitions for the input key values? How we call them? Yes? The splits, exactly. So the splits were the partitions for the input key values. Then we also partitioned the intermediate key values. And then the outputs are also partitioned explicitly as files, part 1, part 2, part 3 on the disk, right? By the way, regarding the partition of the intermediate key values, which is the tricky part of MapReduce, there was an excellent question on the Moodle forum regarding when we say we sort the intermediate key values. And so I wrote a very long answer on the forum, and I really recommend that everybody tries to read this. It's a very long answer. For the people who already completely understand everything, that will strengthen your knowledge even further by really understanding these things. And for the people who might not yet understand everything, that could also help you get a clearer view on what's happening, right? So essentially what I'm explaining is that when we say on the logical level that we have this map and this reduce and then the shuffling in the middle where we sort the collection of intermediate key values, that's only a logical concept. Because in fact, physically on the cluster, there is never, ever, anywhere, any collection of intermediate key values that is sorted. You will not find that anywhere in the cluster. It's only a logical thing. The only thing that you'll have on the MapReduce cluster are subsets of these key values that are sorted, right? So small subsets for a specific map task, for a specific reduce task, but you never have a huge collection of sorted key values, intermediate key values. And in fact, this is what is meant with materialization. We never materialize that huge collection of intermediate key values. It's only a logical thing that we emulate kind of with the shuffling, but we don't build it. So I recommend everybody go to the Moodle forum and read this very long answer that would push you to the next level in terms of understanding what's going on. And I do hope that one of you might even invent the MapReduce implementation on a quantum computer, right? That would be really a huge breakthrough if somebody managed to do that. All right. So now that we have our RDDs, resilient distributed data sets, what do we do with them? Well, three things. That's just like the cycle of water. You see water evaporates, then it turns into clouds, then it's raining and it falls back to Earth. Here it's the same thing. The evaporation of water, that's the creation of the RDD, right? You have the data sitting on HDFS, on S3, on your disk, or maybe in your memory as Python lists, for example. Then you create the RDD. Then you have an RDD. Once you have created some RDDs, you can transform them. So then this is the transformation. That's this list of 30 ways that you can transform RDDs, right? Filter, map, flat map, and so on. That's the second thing you can do. And the third thing, and that's when it rains again, that's an action where you take, after transforming according to the DAG, you take the RDD and then you act on it. So you can, for example, print it on screen, which is a materialization, by the way, or you can write it on disk, which is also a materialization that you write it down to HDFS, to S3, or to your local file system. So creation, transformation, action. These are the three things that you can do. And so now you can see on this DAG, directly the cyclic graph, this is the creation. So here I create one RDD. Of course, I could create multiple of them, right? That would still be a DAG, right? But in that example, just I create this one. Then you have all of these transformations all the way here. But if all you do is you create RDDs and you transform RDDs, in fact, nothing is going to happen on the cluster. It's just quiet and no data flows anywhere. But the moment you decide to act and to have an action and to request the materialization of the data right here, then suddenly the whole cluster gets into motion with the data flowing over the network cables, the data spilled on this, data merged and so on, and all the data going all the way to materialize your output on this core on your screen. So it's a lazy evaluation, right? You don't do anything until there is an action, and when there is an action, then the whole cluster sets itself into motion. Who is with me? Right, very good. Now, a few more concrete details, and I'll show you an example, is that you can use many languages. You can use Scala, Java, Python, and so on. Scala is the native implementation, so MapReduce, Hadoop, it's all Java, but Spark is in fact Scala, right? Spark, for the context, it was created at Berkeley, and then they created a company called Databricks. Who heard of Databricks? Okay. Oh, I have good news. There will be an engineer from Databricks who will come in roughly 2 weeks to give a guest lecture on lake houses and so on. So you should be there, probably on the Wednesday morning in 2 weeks, right? So Databricks is basically the company behind Spark, and Spark is open source. So it's written in Scala, but you can also use Java or Python. You can write a whole application on it with a lot of computer code, or you can have a shell or a Jupyter notebook and just write your creations, transformations, and actions in your Jupyter notebook and see the results. In fact, this is what we have in the exercises and what we have on the exam. It's going to be writing Python code in your notebook and seeing the results of your actions. It's called PySpark, the Python implementation. Here's a concrete example of PySpark, and this is something you could put in your Jupyter notebooks right here. So I'm creating, that's a creation, a first RDD. I create that RDD based on a Python list. So I have a Python list that's like a JSON array. Of course, it's so small, that's not big data at all, right? But I have this list of 2 strings, hello world, hello there. When I invoke the parallelize creation, that's going to turn it into an RDD. Now I have an RDD with 2 strings, right? That's what I wrote as any values. Well, in that case, the values are strings. SC here means Spark context. That's just some object that you create at the start when you start using Spark, but at the exam, you will just have this for free in the Jupyter notebook, right? So you have your Spark context, and then you create that RDD. I put it there, but I put these dashed lines around because that's all lazily evaluated, because I don't have an action yet, right? Then I have a second RDD that I obtained by using a transformation on the first one. So it's rdd1.flatMap. What am I doing? Well, I need to specify how I map, right? So what I'm doing, it's called a lambda, right? So who heard about lambdas? Right? So you know, right? So it's basically a function that you pass to the flat map. And that function tells you that every value that comes from here will be split according to spaces. So there's a space here, there's a space here. So you split that into these 2 parts, you split that into these 2 parts, but it's a flat map. So you flatten everything again, and then you have these 4 strings. Again, I put the dashed lines in here because at that point, nothing happens, right? Mathematically, that's the intent, but it's lazily evaluated, so nothing happens. However, if I now invoke an action, this is an action that counts by value. This is going to give me a Python dict that has all the unique values mapped to the number of times they appear. So you see hello is twice there, so I have it here. Now the dashed lines are gone because the moment I press enter, then the whole thing sets into motion, and I get this Python dict back that contains this materialized output, nicely printed on my screen. Who is with me? Right? So that is a simple DAG because in that case, it's just only one step in the DAG, right? But of course, with the power of object-oriented programming, you can see how you can create all the RDDs you want and transform them in any way you want, right? So that was the hello world. Who is still with me? Okay. So that is how to use Spark. And if you just use it in that way, it just feels like magic, because you're just sitting in front of your notebook and writing code, and things just happen magically. at that point, it's just a logical considerations that I'm showing to you. Then we'll talk about the physical implementation. Now, you correctly saw in the game of differences that there were 3 differences, and one of the differences was that instead of just map and reduce, we have 30 plus different transformations. It's like a restaurant menu, right? You go to the restaurant or to the Mensa, and then you have all of these possibilities. So I'm just going to present the restaurant menu to you, everything that we have here on the menu. So I'll start with the easiest transformations. We just take a collection of values and turn it into a collection of values, right? So one RDD turned into one RDD, and this can be RDDs of anything, integers, strings, dates, JSON objects, and so on, even key values, anything. Here's the first transformation. The first transformation is called filter. Filter needs a function. It's a yes-no function, a predicate that says yes or no, you accept this value as making it through the filter, right? So in that case, I have an RDD. The function is evaluated on every one of the values. You can see that 6 of them return false, so the function returns false for them, and 5 of them pass the filter, the function returns true. And now we say that the output of that transformation is a new RDD with these 5 values in here. Who is with me? Right? So this is a filter transformation. You probably see here how this is somehow a SQL selection, right? If you would like to implement SQL on top of that, that's basically a selection where you pass a selection predicate as the function. The function, by the way, is also a lambda, right? In your code, that would also be a lambda. Here's another one. It's a map function, so you also pass a lambda in there. That function takes one value and returns one value, right? So you see here, that value, for example, was converted to that value. Note that the value here might be structured. That might be an object, that might be an array, a list, and so on, right? But it is one value, right? So you map it, so you have for every value in here, you have a value in there. That is a map transformation. Who is with me? Right, so that should be very, very intuitive. Here's another one, that's the flat map. So the difference with the map is that the flat map, the lambda that you pass to the flat map might return 0, 1 or more output values, and you flatten everything again. So that means that, for example, on here, you have a value where the function returned 4 different values, but it's flattened. So at the end, all of the values that are output are just on a flat line. So it means that then you forgot where they came from, right? It's just, again, a flat collection of values. Who is with me? Okay. Here's another one. This transformation is called distinct. It takes an RDD, it compares the values, and it outputs it eliminates duplicates, basically. It will compare them and only output every distinct value just once, right? Who is still with me? Right? At that point, it's relatively easy, right? Conceptually, we just have ways to create an RDD out of another RDD. Quick note, do you see here the spaghetti? It's spaghetti, right? But here there's no spaghetti, right? That will be important later for the shuffling, because you might start guessing here. We're supposed to only discuss logical things, but if I anticipate a bit on the physical aspects, there will not be any shuffling here, no shuffling, and here we'll probably need to shuffle a bit. Right. So I'll come back to that. But since we only deal with logical aspects right now, we shouldn't care about the shuffling, right? But I'm just noting that. There is another transformation that takes a sample. So you pass some pseudo-random function with a seed, and that pseudo-random function is going to be called, and basically every value you create a Boolean at random, you pick a Boolean at random. If it's yes, you keep it. If it's not, if it's false, you don't keep it, right? So it's a little bit like a filter, except that the predicate is just a random generator, right? Who is still with me? Right, very good. So the seed here is because it's pseudo-random. Pseudo-random means it's not actually random, but it simulates randomness, and the seed allows you to somehow control that randomness. All right. Okay, so these were all transformations turning one RDD into one RDD. Now we have more transformations that take two RDDs and turn it into one RDD. That we didn't have in MapReduce. Here's an example. We could take two RDDs and compute their union, right? So it's going to be just a concatenation of them. At that point, I should perhaps mention that RDDs are ordered, right? So there is an order in which the values appear, and some transformations preserve the order, like filter, map, and so on. They will keep the order. Some other transformations, when they shuffle, might no longer guarantee any order. So for example, for distinct, the order could be pretty much anything here because it's been shuffled around. But here, in most cases, you will have all of these values coming from this RDD, and then all the values coming from that RDD, right? So first this, and then this. I open a small parenthesis for those of you who are very comfortable and everybody else just forgets what I'm about to say. There is a special case in which these two RDDs are partitioned exactly in the same way. They have the same number of partitions, and the partitions match one-on-one on every machine. In that case, you will not get an order like this, but you will get first partition from the left, first partition from the right, second partition from the left, second partition from the right. So there is a few special cases in which the order here might interleave the values coming from the two sides, right? So that's a data independence breach, because normally we are not supposed to see what's happening on the physical level. Parenthesis closed. So if that confused you, just forgot what I just said. But generally, in most cases, you will have the values from the left and then the values from the right. Who is still with me? Right? That is the union. Then we have the intersection that basically is going to output the values that are both on the left and on the right. Who sees the spaghetti? Right? This is going to shuffle things around. There's no shuffling here, but here there will be shuffling on the physical level. Then we have subtraction, right? When we are going to output all the values from the first RDD that are not in the second RDD, right? Note that these three, union, intersection, and subtract, are part of the relational model in relational databases, right? You can say in SQL, select from where, union, select from where. You can say intersect, and you can say except for the subtraction. So this exists in SQL, right? So this is also a way to implement this SQL construct physically. And now the scariest of them all, the Cartesian product. So you basically have a first RDD, a second RDD, and you compute all the possible combinations, all the pairs. Now what I would like you to see to realize how dangerous this is, imagine that we have 1 billion values in the first RDD and 1 billion values in the second RDD. How many values will we get in the Cartesian product? A quintillion values in the Cartesian product. So what's going to happen is the cluster is going to crash. This is what's going to happen. And it is so dangerous that by default, Spark does not allow you to do that. There is a property that you can configure that forbids the Cartesian product, that completely deactivates them. And you have to manually activate them if you know what you're doing. And you know that you're not going to crash the cluster because you know that the RDDs are not too big or one of them is small, for example. Okay. Yes? Mm-hmm.
A union between two RDDs and both have a value that repeats itself in both of them. It's going to be just like a union of sets where only one of them will be in the result, or is it going to be like a string concatenation?
So basically, if I summarize your question, you're asking if that's a pure concatenation without duplicate eliminations, or if we eliminate duplicates, right? We do not eliminate duplicates, right? This is really like a concatenation where all the values here are here, all the values there are there, and the total number of values will be the sum of the number of values in here and in there, right? So we don't eliminate duplicates. The explanation of that is just that we don't want to shuffle in here. We want to keep that plain simple. if we wanted to eliminate the duplicates, we'd have to shuffle things, and that would be more costly, right? So you can really view it for all practical purposes, and in most cases, as a simple concatenation, right, of values. Okay. Does that answer your question? Yeah, awesome. Union, intersection, subtract, and the scary Cartesian product, be extremely careful. If you ever do that at the exam and it crashes your machine, don't worry, we'll sit you on another machine, right? So you can raise your hands, we'll fix things, but still it distracts, so it's better not to do these things, right? So be careful and mindful of what you're doing with the data. Okay? So these were the transformations. There's roughly 30 of them, right? So some are listed in the documentation, but if you want to see all of them, you need to see the Java doc. So there are some pages that list the methods that you can call on the RDDs, and then you can see the whole list. It's roughly 30 of them. I didn't show them all, of course. But as we saw, lazy evaluation, so if all we do is transform RDDs, nothing is going to happen on the cluster. So the crash of the cluster is not going to happen when you invoke the Cartesian product. It's when you invoke an action to materialize the Cartesian product that it's going to crash. So what actions do we have? The simplest of them all is collect. It's basically the identity function. Logically, it's the identity. But physically, that is a materialization of the RDD. It means that it downloads all of the values from all over the place and materializes them on your computer as a Python list or a Java list, right? So this is why we say it's a materialization. Now you have a physical list in your memory that contains the values, right? So this is what collect does. Who is with me? Right? Okay. Then this is another way to materialize. It's materializing on disk. So this is called save as text file. There's others, save as sequence file, and so on. You basically save the RDD on your local drive or on HDFS or on S3 and so on. Now, the difference between the two is that collect is also something to be careful about, because if you are about to collect an RDD with 1 billion items, that could crash your machine, right? If you know that the RDD only has 10 items, then you can call collect. Save as text file will not crash your machine, except if you try to save on your local drive. With the file scheme. But if you try to save to HDFS or S3, that's not going to crash anything because of the power of parallelism. Because the save as text file will be done in parallel on all the machines. They will each materialize their share, their partition of the RDD, right? But this is technically also the identity function. It's just that it puts it on the disk. So we materialize, right? Who is still with me? Okay, let's move to the next one then. This is an easy one, counts. So counts is just outputting a single number, which is just the total number of values that you have in your RDD. As you can imagine, this is easy to optimize from an implementation perspective because you're just asking each machine in the cluster to count how many they have locally, and then you just ship the numbers and compute the sum, right? So that's an example of push down, by the way, because you don't download all the values. You push down the counting to each machine, and then you only download the aggregated values, so the counts. Okay, so that is the action count. Then we have the action count by value. So this returns an integer. Count by value returns a Python dict. It returns a Python dict that has as keys the unique values, and it has as values the counts. So here there's a 12 blue values, 4 yellow value, and 6 green values. So that's a Python dict that says blue colon 12, yellow colon 4, green colon 6, right? Be careful, because that's going to work if the unique values, if there's not too many unique values, like 10, 20, maybe 1,000. But if your RDD contains 1 billion unique values, you're basically asking Spark to build a Python dict with 1 billion keys. That is also going to crash your machine, right? So always be mindful of what you're doing when you invoke an action like that, right? So this you should do if the number of distinct values is small enough. Now, if you cannot call collect because there's too many items, there's too many values in your RDD, you can limit the items you take. You can take, for example, only the first 4 items, the first 4 values, right? So that's take 4. That is a bit like the limit 4 in SQL, right? When you don't want to see the whole table, but only the first 4 records. So we say take 4, and then it only downloads and materializes the first 4 values. Then we have top. Top is going to logically sort the values. You have some comparison function that tells you which values are larger or smaller. So with integers, it's obvious. With strings, lexicographic, and so on. And that returns the maximum 4 values. Now, if you know a bit of complexity theory, that sounds like n log n, because you have to sort and then take the top 4. But in fact, if you use a heap structure, you know that you can use a heap structure to retrieve just the top values, and that becomes linear almost. Right? So this is, and on top of that, we even have parallelism, right? So this is the first 4, and this is the highest values, the highest 4 values. Of course, 4 is just a number. You can put whatever number you want. If you don't like 4, you can put 42 or whichever numbers you would like to have. Take sample is like take, but it's just randomly picking values, right? It will just draw 4 values at random from your RDD. But the difference with the sample transformation is that this is an action. So when you take the samples, you actually materialize them to your machine, right? You will have them sitting in a local array, Python array on your local machine. And here's yet another action. If you have a binary operator like plus, like multiply, like min, like max, then you can use reduce, and it's just going to use that operator pair by pair. So it's associative. Normally it should be associative and commutative. And it's just going to aggregate all of these values into a single one and return that unique value, right? Who is with me on the actions? Right? So this is the restaurant menu, right? You have all of that, and these are all the things that you can use to collect them into your Jupyter notebook and nicely print it on your screen. Since you're all with me, I'm going to show you even more transformations. Because I told you that the RDDs can be RDDs of anything. RDDs of integers, RDDs of JSON objects, RDDs of JSON arrays, RDDs of strings, RDDs of dates, RDDs of byte sequences, anything. Anything could also be a key value. So it means we could also have RDDs of key values, right, of pairs. So there is special transformations that specifically are meant when your RDD is an RDD of pairs, an RDD of key values. One such transformation is called keys. So when you have an RDD of key values, it's just turning it into an RDD of just the keys. So you drop the values, basically. You just keep the keys. And the other one is values, where you drop the keys and you just keep the values. Who is with me? Right? So these are relatively simple ones. Here's another one that's called reduce by key. Again, it needs to be a pair RDDs for this to work. So reduce by key is going to take all of the unique keys that you have in here, and it's using some associative and commutative binary operator, like plus, but it could be min, max, or whatever you want. And it's going to output key value pairs, but now all the keys are unique. And this is the aggregation with whatever associative commutative operator you put in here. This plus this plus this plus this is the value in here. Reduce by key. By the way, at that point, who could tell me how you can emulate MapReduce? Which 2 transformations do you need to use to emulate MapReduce? Which transformations does the map and which transformation does the reduce? Let's start with the map. What Spark transformation would do the equivalent of the map in MapReduce? Yes? Just map. So we have, you say map. Anybody else? Yes? Flat map. Okay, anybody else? So let's do a vote. Who thinks it's map? Who thinks it's flat map? Right? So flat, it is indeed flat map. Remember that the map function in MapReduce returns 0, 1, or more key values. So we flatten in MapReduce. So it is true that it is in fact flat map. There is a bit of a trap in here. So it is flat map. And what about the reduce function? Yes? This one on the screen. Yes, you correctly guessed. This is why I'm actually asking the question. And here too, the trap is that it is not reduce, because there is something called reduce in here, Where is it? Oh, here. That's not the one. So it's not map and it's not reduce, right? So it's really flat map and reduce by key. This is how you basically say that's a generalization of MapReduce, where the RDDs are pairs and all you do is a flat map followed by reduce by key. Then you got your MapReduce. Who agrees with that? Very good, okay. Then we have group by key. Group by key is a bit similar to reduce by key, except that it doesn't aggregate anything. So basically, if you do group by key, it's going to still output the unique keys, but here you have an array nested inside that key value. You have an array that contains the individual values in here, right? So this is group by key, and then you can do something with them maybe later. Then you have sort by key, which is just sorting all of these key values by key. I didn't know how to sort colors, so I sorted them by wavelength. So I hope that's okay. So here we just provide a comparison function, and then we sort them. Then we have map values. So you provide a lambda that maps, it preserves the key, but it changes the value to another value. So that's again a lambda that maps the values. You have joins also. In fact, you don't only have joins, you have also left outer join, right outer join, and full outer join, right? So what happens is that you try to match the keys that are the same. So you hear there's a match right here, there's a match right here, and there's a match right here. So that gives it, oh, there's also one here, right? So you match, and that's all the possible combinations. It should remind you of the join in SQL with relational tables. Right? It's just that we abstract away the relational table as just the keys and the rest of the columns are just the values. For whom is that natural? Right? So this is a join, and we have left outer join, right outer join, full outer join. So you see this is yet another example on how you can actually implement a language like SQL on top of this. Let me check the time. 3 minutes. I just cannot start anything new, but showing you the menu is fine. We can subtract by key. That's just eliminating the key values where the key is not on the right. So where it is on the right, sorry. So we eliminate the blue because the blue is here. We eliminate the orange because the orange in here, and only this one survives, right? Subtract by key. Count by key as an action is generating a Python dict that is going to count how many times the key is actually occurring, right? So this is similar to count by values on generic RDDs. This one is specifically on pair RDDs, right? Lookup. So again, that's an action. That was a transformation. Now these are actions. So these actually download things to your Jupyter notebook, right? So that's a Python dict. This one, lookup, is you provide a key and it fetches the values with that key. So in that case, if you say that key orange, you get that value and that value. And again, you download them. It materializes them to your local machine in your Jupyter notebook, right? And I'm done with the restaurant menu. So it wraps up the things for today. So what I've done so far is just the logical level. I've just explained to you how to use Spark and how we just have a DAG of transformations. And next week, I will explain to you the physical implementation using parallelism and batch processing on the cluster. As we will see, it's very similar to MapReduce, just even better. So thank you, everybody, for attending, and I see you next week on Tuesday at 2 p.m. Thank you very much.